Greetings. My name is Three Hoods, and I am the last living human on the planet known as Earth. Today I'm going to talk about the Flax Capacitor and how it works. But first let's do a little review of the rule of omega. Vir must always be satisfied. In a circuit with a battery of 10 volts and a single resistor of 1000 ohms, the current is easily calculated at 1 centiampere. If I use two resistors of 500 ohms each, the total resistance and therefore the current are the same. If I test the voltage at a point between the two resistors, intuitively it's easy to see why that would be 5 volts, but it can also be easily calculated. With a current of 1 centiampere and a resistance of 500 ohms, each resistor would have to dissipate or drop 500 centivolts. If I made this second resistor very large, let's say 1,000,000 ohms, the current would be tiny. But if I did the same as before to calculate the voltage dropped across each resistor, I would find that almost all of it has to be dropped by the large resistor, and the voltage at this point between them is almost the same as the supply voltage. Remember, this is how electronic signaling works. A high voltage, one that is close to the supply voltage, represents a logic high, or logic 1, and a low voltage, close to ground, represents logic low, or 0. Logic inputs generally have a very high resistance to enable this kind of control, and outputs behave similarly to the positive supply when logic high, and similar to ground when logic low. So, from last time, here is the schematic diagram of the Flax capacitor. I'll break this into 3 sections, and I'll replace the diagram symbols with totally realistic images of what the components really look like when you are looking at them in reality. In the output section, I have 2 lights connected to the outputs of the logic section. When an output is high, it will light up the light. The lower one is also connected to the green Tesseract wire, so the Tesseract will activate whenever this line is low. On the opposite side, I have 2 resistors and my 2 beepity beeps. When the switches are open, there should be close to 5 volts at the logic input, but when the switch closes and shorts to ground, the 5 volts are dissipated by the resistor, and the line goes low. This, by the way, is called a push-up resistor because it pushes the signal up to the supply voltage. That's what it's called. Look it up. Do it now. So how about this midsection? It's not really a midsection, it's more of an upper torso, really, a rack, as it were. Anyway, this part is called a flip-flop. It actually isn't a complete flip-flop, it's only part of one, but it functions the same way. These 2 thingies here are called NAND gates. And they normally come in a funny little black box that you can't open up. If you were to open it, though, it would look exactly like this. This is what NAND gates look like. What they do, in simple terms, is they output a logic high signal all the time, unless both of their inputs are also logic high. So what happens? Well, with the gates outputting a logic high, and both switches open, this means all the inputs are high, and the gates will output low. When the outputs go low, the gate's input condition is no longer met, and the outputs have to go high again. They keep doing this over and over at the speed of light, causing a rupture in the tissue of time-space, and the universe implodes. Clearly that isn't what happens. In real life, many factors affect the speed at which these signals propagate through the device, and basically one signal gets there faster, so the flip-flop will end up in a stable state with one output high and the other low. Kind of like this. When I press the buttons, this changes which of the outputs are active. It's like an electronic version of the flippity switch. Now, I do realize that the Tesseractivator only gets me the power I need for the time machine. I still need to figure out how to build an actual time machine. So if you have any advice in that arena, please leave me a comment. I'm kinda lost here. Don't know what I'm doing.